Thanks. So I'm Richard Osborne from XMOS. So we're a UK fabless semiconductor company. Developed a processor, the XCore processor. It's aimed at embedded market. I guess the main feature of this processor is it's been designed to allow you to implement what are traditionally hardware interfaces, but from software and from a software-based design flow. So there's a list of some of the things that we already have code for that we can do just in software. So I'm going to be talking a bit about the architecture and a bit about what we're doing with LLVM. So first off, what does a processor look like if you design it to implement hardware interfaces? So the main feature that lets us do that are we've got something we call ports. So the job of a port is to take data from I/O pins and present it to the processor, and similarly take data from the processor and drive it onto a collection of pins. But it's not just a straight mapping, there's some configurability there to allow you to offload common tasks onto the ports, which kind of execute in parallel with the processor. So an example of something you can do with a port is there's a buffer in the port, so you can queue up outputs to happen at some time in the future. You can configure a port with a clock, so that inputs and outputs happen on clock edges, and you can configure a port so it serializes and deserializes data. So you might have a 1-bit serial interface that's going very quickly. You can deserialize that into, say, 32-bit chunks. So you can deal with the 32-bit chunks at a lot slower rate, and it's a lot easier for the processor to deal with. So because the kind of real world is parallel, we want to kind of we have these. The processor supports multiple threads in hardware, so this allows you to dedicate a thread to a particular task. Because if you're doing something with a hard real-time requirement, you don't want to have to context switch. So you can dedicate a task to, say, just do Ethernet, get the data in, and then you pass it on to another thread, which maybe does some processing, and passes it on to another thread, which then maybe outputs it somewhere else. So with the threads, you need a way to communicate between them. So we've got hardware support for that through channels. So essentially a channel is a connection between two threads. You input on one thread, that will block until the other thread does an output, and then you receive the data. So it provides synchronization and data. The XCore has been designed to be deterministic. So what I mean by that is, if you take a sequence of instructions, you want to be able to reason about its worst case performance. So the implementation of the thread scheduling and instruction fetch and memory fetches means that one thread can't interfere with another thread's execution. So you could have one thread which is kind of constantly doing memory reads and writes, and that won't affect the performance of another thread. There's no caches, so memory access is deterministic, and there's zero penalty branching. So a branch instruction actually fetches its execution, and you can execute code on the next cycle. So now I'd like to talk just a bit about our tools, and this is the state of our toolchain today. So we've got we're using LLVM GCC for our C and C++ compiler. That's been shipping in our toolchain for about a year, and it was a quite easy port but at the moment we're just using it for plain C. So we haven't extended it to, it's got no support for the kind of particular hardware features like channels and ports. It's just basic C, arithmetic, control flow, things like that. In order to target the hardware features, we've got a separate language and separate compiler. So the compiler, it's the XC language. The compiler was developed from scratch, in-house, and it was developed alongside the architecture. It's got support for explicit parallelism. It's got dedicated operators for input and output, and it's designed to allow a number of compile time safety checks. But because of that, the language is a bit restricted. So, for example, we don't allow pointers, we don't allow aliasing. But that allows us to check a number of things at compile time. So what I've been looking at recently is to extend the C compiler to target the XCore hardware resources. So there's a few reasons why I want to do that. So first of all, the XC language, for some people it's a bit of a barrier. So, you know, I've got to learning a new language, so they may not even, before even looking at it, we find that kind of once people do start using it, they kind of, actually there's quite an easy learning curve, but we want to make things as easy as possible for people, so we would like to allow people to target these things from C as well. Kind of I guess a long-term goal would be implementing these extensions in C gives us also a good idea of how easy it would be to retarget our current XC compiler at LLVM, so it went through the LLVM backend. And also, it allows the two languages to interact better. So if you've got support for channel communication in C, you can have a C thread and XC thread, and they communicate over channels. At the moment, that would have to be done through a function call. So you'd make a function call from C to XC. So yeah, that's what I'm going to be looking at. So at the moment, this is kind of in the prototype stage. There's no release date for it, but hopefully this will make its way back into the toolchain. So for this project, we already had a LLVM GCC port, and we're using that. But kind of decided that actually extending the front end of that it would be a lot of work, and we're better off actually using Clang for this. We didn't have any support in Clang for the XCore, but adding it was actually very trivial. It was less than 100 lines of code because we already had the LLVM XCore backend. There really wasn't much work to do there. And its design, the kind of library-based design where there's clear interfaces between the different parts of the front end, makes it easy to kind of understand the code and add extensions. The interface for these features is we kind of group them all together under the title resources. So there are three main resources. So ports I've already talked a tiny bit about, which provide access to pins. There's also timers, so you can kind of wait for specific time periods or measure time. Chan ends, two channel ends form a channel, and all of them they follow a very similar usage model. So you can think of them all as just streams of data. And the instruction set presents them in a very similar way. So I'm gonna mainly focus on port I/O, not because the other two aren't interesting, but because if you understand port I/O, then you kind of understand the other two as well. So So resources are referred to via resource identifiers, which is a 32-bit integer that uniquely identifies that resource. That's given as an operand to any instructions that operate on that resource, and it can also use to pass that around as a handle between functions, just as a normal variable. So got the different types there. And two basic operations, and these are supported directly in the hardware by an input and output instruction, are input, so that would be sample a value from the port, get the current time, or receive some data from a channel, and also output, drive value onto a port, or output a value onto a channel. There's no outputting to a timer. That wouldn't make much sense. This is an example of using port input in this case. So in the XC language, we've actually have dedicated operators for input and output. But for the C extensions, we wanted to keep it wherever possible. We didn't want to extend the grammar. We just wanted to make things look like function calls. So in this case, we've got a port input function call, which reads the current value on the port. And then there's a port input NE, which stands for not equal. So you can do some basic kind of pattern matching on ports. So you can wait for certain conditions to become true. So in this case, this function is waiting for a transition on a port. So it gets the current value with the port input, and then calls port input not equal with that value, which will cause it to wait until the value changes, and the new value will be returned. So this is what it looks like in the instruction set. So you see the input instruction performs the actual input, but just before the input instruction, you've got this set C. So set C, each port has a bunch of state, and the state of the port determines how the input instruction behaves. In this case, the set C instruction is setting a condition. The first input is unconditional, it just gets the current value. So we do a set C condition none. The second input is, there is a condition there, so we do a set C condition not equal. A set D to set the data value that it should be comparing against, and then do the input. So there's this kind of configuration of port state, and then input instruction to actually perform the input. So that's just a summary of that. So the input instruction will block until the input is completed. So whilst that example could be implemented just as library calls, there are some good reasons why actually having compiler support for this can give you a much better code. So what we've done is added Clang built-ins for these, which map to LLVM target intrinsics. And then in the XCore backend, those trivially map to the actual instructions in the ISA.
Question.
Yeah.
So why not have implemented the instructions at the source language level as function calls, and then implement the function calls directly in LLVM IR?
So just recognize the function calls by name, do you mean? Or?
No. What I mean is that so you make port input, for example, be an external function call.
Yeah.
You implement it in LLVM IR, so you just write it directly in LLVM. You then then you compile your program which calls port input. You compile the library written in written directly in LLVM that implements port input.
Right.
You link them together and then you inline.
I see.
Does that give you the same result, or is there another reason?
It would for this example. Something else that I'm going to come to later on. It means that the compiler front end actually needs to understand these input functions, or input built-ins. So it should become clearer as I go on.
Okay.
Hopefully.
Another question I had is: are these the only port input instructions that you have?
No. So there's actually quite a large number if you enumerate them all. I didn't want to kind of get bogged down in detail. So there's port input equal and not equal. There's also you can time. For each operation can be timed. So you can do. So if a port is associated with a clock, then essentially there's a counter going on the background such that every tick of that clock it's incremented. So you can specify that an input or output should happen at a particular time. So there's a built-in for that. Similarly, you can get a timestamp of when an operation happens. So you might be waiting for a condition, and you might want to know when that condition was met. So you can get that. So there's actually a whole bunch of these functions, but I just wanted to concentrate on one or two. So one of the reasons why, one of the benefits of having compiler support for these operations is you can do a number of optimizations. So we've got this setup where you configure the port state and then you perform the input. Well, the port state is persistent. So if you've got multiple configuration instructions which are setting the same condition or setting the same data, you can eliminate all but one of them. So that's the first case there, of just eliminating the set C, which is redundant in that case, and also you can hoist them out of loops. So again, there's a set C there. It's in a loop, but there's no reason why you can't move that set C out of the loop to just before the loop, saving the instruction. So you can actually get quite far just by kind of adding built-ins and intrinsics, and the translation at each point is quite straightforward. But there's another feature of the hardware that kind of requires a bit more support. So normally an input will just wait until one particular resource is ready. The architecture also supports waiting for one of a whole set of resources. So example of this might be you could wait for an input to complete, or you might or a timeout on a timer to occur if it might be the case that the input may never complete because the other end isn't there. So to support this, we've extended the Clang front end with support for this select statement. We tried deliberately to make it look like a switch in C. The rules for what can go on a case are slightly different, though. So a case must be either an input built-in or an assignment with the input built-in as the right-hand side. So the semantics of this statement are that it sets up the conditions for each of the inputs, and then it pauses until one of them is met. And at that point, it jumps to the corresponding case and executes that code. So we kind of describe this as kind of event-driven programming, and describe XCore is kind of an event-driven processor, because it's just been designed such that you don't poll data. You kind of set up everything you're interested in, and then wait for pause. The thread pauses, so you can kind of save power, and then as soon as something happens, you jump straight to the piece of code to handle that. And that's very efficient, so you get very low latency, can respond very quickly. So this is what that previous example compiles to. We've got the set C and set D that we've already seen. There's additional state setting instructions, EEU, which is event enable unconditional, and set V, which is set vector. So EEU, that configures a resource such that it will event when the condition is met. And set V associates an address with that resource, so that when the condition is met, it jumps to that address. So we set up all the state and then do a wait EU. That pauses the thread, and it will then vector to the when one of those becomes ready, an event will be produced, and that will cause it to vector to either case 0 or case 1, depending on if it gets the data or if the timeout happens. So it's not obvious. It wasn't obvious initially how to model this in the LLVM IR, because in the LLVM IR you can't take the address of a basic block. So you couldn't model the set V, the set vector instruction, as an intrinsic. But the observation is we've kind of made the select statement look like a switch in C. So the idea is actually model it in the LLVM IR as a switch, which is kind of implemented in hardware instead of with a jump table or comparisons. So we introduced a intrinsic LLVM XCore select, which takes a variable number of resources, and all it does is return an integer to say which one of those resources in that argument list is ready to event. So this is what the example looks like in LLVM IR. So we have this select, and it's used directly as the operand for a switch instruction. We then match that combination in the XCore backend, and in the XCore backend we can then kind of produce the code to, at that level we can deal with the address of basic blocks, and we can match that combination to the code to set up the vectors, and then wait, and then the hardware will jump to the right place when an event comes along. So I guess there's one limitation of the current implementation of our current implementation is that all the resources which can event must be listed as arguments to this intrinsic. Now this prevents us. That means that the list of resources has got to be known at compile time. That prevents us doing things like selecting over an array of resources where maybe the number of resources comes in as a parameter. So we'd like to support things like this, but at the moment we can't do that. And we've been thinking about kind of how we might implement this. So I suppose our thoughts were, this is a wish list item. It would be nice if you could take the address of a basic block in the LLVM IR, and then this would allow us to model this. So be very interested in hearing people's thoughts about this, and if it might be useful for other people. I know the GCC extension of computed go-tos at the moment kind of has to be lowered to switches on integer indexes. So maybe that could, there's similarities between the two. So, okay, so we've seen that actually LLVM allows most of the processor's kind of unique features to be modeled simply through intrinsics, and that gives enough information such that we can optimize at the LLVM IR level. The select and the kind of event-driven programming we can model as a kind of hardware switch, but there is a limitation in that we can't select on these kind of arrays. So that's something we would like to improve in future. Okay.
Thank you very much.